The goal of this lecture is to examine orbital motion in Schwarzschild spacetime, so the metric is ds squared equals minus 1 minus 2m over r dt squared plus 1 minus 2m over r inverse dr squared plus r squared times d theta squared plus sine squared theta d phi squared. And the context is our own solar system, so the m that appears here is the mass of the Sun. And what we want to do is examine the orbital motion of the planets about the Sun. So the planets are all material particles, so they follow time-like geodesics. So we'll be dealing with the time-like case, and here are the geodesic equations. Now in an earlier lecture, I derived circular orbits in Schwarzschild geometry, but this time we'll be examining the orbits that in Newtonian gravity are elliptical orbits. So we'll be looking at the general relativistic versions of the elliptical orbits. Now we could try to solve these equations directly. We would probably have to do it numerically, but either analytically or numerically, what do we have? We have these equations, the geodesic equations themselves, are a set of 4 second-order differential equations. So that means we're going to have 8 integration constants. And those 8 integration constants can be determined by 8 initial conditions. The 8 initial conditions would be the initial coordinate values and their derivatives. So at parameter value 0, we have the x mu's and the x mu dots. But we also have the normalization condition, and I'll remind you that's just it's just the norm of the derivative here, the norm of the 4 velocity in the case of a time-like geodesic. And this expression is a constant of the motion. So this, by virtue of these 4 equations, this is always a constant. So all we're doing is just picking that constant to be minus 1 initially. So the initial conditions are not entirely free. They need to be chosen to satisfy the normalization condition. So we choose these 8 bits of information to satisfy x dot mu at the initial parameter value times g mu nu, and that's of course a function of x at the initial parameter values, times x dot nu at parameter value 0 equals minus 1. And then once this has been chosen initially, the fact that this expression is a constant of motion means it will remain equal to minus 1. Having chosen the initial conditions, we can then integrate the geodesic equations themselves to obtain t, r, theta, and phi as a function of the parameter in this time-like case being the proper time tau. And in most cases, the integration would need to be done numerically, but that's not too difficult. You can use your favorite integration routine like, say, 4th order Runge-Kutta. I'm not going to use this direct approach to solve for the time-like geodesics. Instead, I'll make use of a very useful result that holds for any geodesic in a space-time with symmetries. So let's consider a space-time with some symmetry. That means there's a killing vector field, k. So k is a killing vector field. And it has the property that the Lie derivative of the metric along the killing vector field vanishes. And now this can be written, it's not too hard to show. This is equivalent to del mu k nu plus del nu k mu equals 0. Now let's consider a geodesic, x mu of tau, and the derivative is, we'll just call that u for the 4 velocity, that's partial x mu with respect to tau, and it satisfies the geodesic equation, which, remember, we can write that as u alpha del alpha u mu, the acceleration of the world line, equals 0. Here's the picture. we have a world line, and the tangent to the world line is u. And we also have a killing vector field. And now the result is that the inner product of u and k along the world line is a constant. So we can write the inner product between u and k as k mu u mu. Of course, that's shorthand for k nu g nu mu u mu. I've just lowered the index on k using the metric, right? This is equal to a constant along the world line, along this geodesic. And that's fairly easy to prove. We just differentiate this function along the world line, and the derivative along the world line we can write as u alpha del alpha of this quantity, k mu u mu. Okay, so now using the product rule, this is u alpha del alpha k mu times u mu plus u alpha del alpha u mu times k lower mu. Of course, this is just the acceleration, which is equal to 0 because the world line is a geodesic. What remains is u alpha u mu del alpha k mu. Now notice what we have here, u alpha u mu is a tensor that's symmetric under interchange of alpha and mu. So we can swap alpha and mu and it doesn't make any difference. On the other hand, this factor, del alpha k mu, is antisymmetric under interchange of alpha and mu. Remember that k satisfies this equation, which is telling us that del alpha k mu equals minus del mu k alpha. So if I switch indices, mu and alpha, here we pick up a minus sign. And anytime you have a tensor, a two-index tensor, that's symmetric, and it's wired together with a two-index tensor that's antisymmetric, the result is always 0. And that's not too hard to see. We can just write this using, instead of del alpha k mu, we'll use minus del mu k alpha. And now pull out the minus sign, but let's reverse the role of alpha and mu. So we'll just let mu become alpha and alpha become mu. So this is u mu u alpha del alpha k mu. So you can see what we have here is exactly minus what we have here. So the only way that these two functions can be equal, the only function that's equal to minus itself is 0. All right, so what I've now proved is that the inner product of k and u along the world line is a constant. It's a constant along the geodesic. And this holds for any geodesic in any space-time with a symmetry, where k is the killing vector field that generates that symmetry. Now let's apply this result to the Schwarzschild space-time. We know that Schwarzschild has a number of symmetries. In particular, it has a time translation symmetry, and that just corresponds to the killing vector field d by dt. So d by dt is a killing vector field. And we also know that Schwarzschild is spherically symmetric. So it has killing vector fields corresponding to rotations about any axis through the spheres defined by t equal constant, r equal constant. This rotation in the t equal constant, r equal constant subspaces. All right, so there are three independent Killing vector fields corresponding to rotations, but we're going to restrict our attention to orbits that lie in the equatorial plane. So those are orbits with theta equal to a constant, pi over 2. And in this case, the only relevant symmetries are the symmetries along the phi coordinate lines. So in other words, d by d phi is our only Killing vector field that is relevant in this case. Let's analyze this result first for the Killing vector field d by dt. So taking k to be d by dt, that's the vector with components 1, 0, 0, 0. And of course the for velocity has components t dot, r dot, theta dot, phi dot. So the inner product between k and u is 1, 0, 0, 0 times the components of the metric times the components of the for velocity. So multiplying these two factors first, we have minus 1 minus 2m over r, comma 0, comma 0, comma 0. And then multiplying by u, that's t dot, r dot, theta dot, phi dot. You can see this is equal to minus 1 minus 2m over r times t dot. So according to our general result, this is equal to a constant of the motion. And we're going to let this constant be minus little e. So we have the result t dot is equal to little e divided by 1 minus 2m over r. Now let's examine the Killing vector field d by d phi. So k is d by d phi. That's the vector with components 0, 0, 0, 1. And the inner product between k and the for velocity u is 0, 0, 0, 1, multiplying the components of the metric and the components of u. These first two factors give 0, 0, 0, r squared sine squared theta. And the components of u again are t dot, r dot, theta dot, and phi dot. So the result of this calculation is r squared sine squared theta times phi dot. And according to our general result, this is equal to a constant. And we're going to let that constant be denoted by little l. Remember, we're restricting ourselves to orbits in the equatorial plane, so theta is always equal to pi over 2, and this factor of sine squared theta is just 1. So our result here is r squared phi dot is equal to a constant little l. Notice the results here and here are first-order differential equations, so they just depend on first-order derivatives with respect to proper time tau. And that's always the case for the inner product between k and u. It's always a first-order differential equation, and in fact it's always a first integral of the geodesic equations. So let's go back and look at the geodesic equations. Here they are. And now, first of all, notice, since we're restricting our attention to equatorial plane orbits, so orbits with theta equal pi over 2, this whole equation vanishes. So we really only have 3 geodesic equations, and these are second-order differential equations. And we've already now obtained 2 first integrals of these equations by invoking this result that the inner product between the Killing vector field and the for velocity is a constant. But notice we have yet another first integral of the geodesic equations, namely this normalization condition, where the constant of integration has been chosen to be -1. So let's go ahead and write down our three first integrals, and they will constitute first integrals of these three non-trivial geodesic equations. So this equation I'll write down with theta set equal to pi over 2, so this term vanishes and the sine squared theta is just equal to 1. So our three equations are minus 1 minus 2m over r t dot squared plus 1 minus 2m over r inverse r dot squared plus r squared phi dot squared equals minus 1. We also have t dot is equal to a constant little e over 1 minus 2m over r, and phi dot is equal to a constant little l over r squared. Now let's use the second and third equation to simplify this first equation. So this becomes minus 1 minus 2m over r times t dot squared is little e squared over 1 minus 2m over r squared plus 1 minus 2m over r inverse r dot squared plus phi dot squared is L squared over R to the fourth, so this is L squared over R squared, equals minus 1. Now we can cancel this factor in the numerator with one of these factors in the denominator, and what we're left with is R dot squared minus E squared divided by 1 minus 2m over R equals minus 1 minus L squared over R squared. And multiplying through by 1 minus 2m over r, we have r dot, and this is r dot squared. R dot squared is equal to e squared plus 1 minus 2m over r times this factor, which has an overall minus sign. So let's change this to minus, times 1 plus L squared over R squared. And now expanding the right-hand side, we have E squared minus 1 minus 2m over R plus L squared over R squared minus 2m L squared over R cubed. And now I'm going to multiply through this equation by 1/2. We'll see why later on. And I'm also going to bring these three terms to the left-hand side. So this term will be minus m over r, remembering multiplying by 1/2. This term is plus L squared over 2r squared. And this term is minus ml squared over r cubed. And that's all equal to e squared minus 1, and I'm dividing by 1/2. So this is one of our equations describing orbital motion. Recall we also have phi dot equals L over r squared, and t dot equals little e divided by 1 minus 2m over r. So these are three first-order differential equations. They're first integrals of the geodesic equations, and we could solve these directly by, say, numerical integration. We just pick initial values for t, phi, and r, and then integrate forward in proper time using our favorite numerical integration scheme. Alternatively, we can use the same approach as is commonly used to analyze orbital motion in Newtonian gravity. So let's remind ourselves how that analysis goes. So in Newtonian gravity, here's the sun with mass big M. Here's a planet with mass little m. And the planet moves around the sun in an elliptical orbit. We can write down Newton's second law for this motion, but we can also write down the first integrals. So the total energy is 1/2 little m times r dot squared plus r squared phi dot squared. So notice here I'm using polar coordinates in the plane, r and phi. So this is the kinetic energy, and then the potential energy is just the Newtonian potential minus g little m big M over r. And we can multiply through by 1 over m. So we can write this as E over little m equals 1/2 r dot squared plus 1/2 r squared phi dot squared minus g big M over r. Now another first integral of the equations of motion comes from angular momentum conservation. And angular momentum is, of course, r cross p. So that's equal to p is mass times velocity. R is r hat, that's r vector, cross the velocity vector is r dot in the r hat direction plus r phi dot in the phi hat direction. Of course, r hat cross r hat gives 0. So this is just m r squared phi dot times r hat cross phi hat. So that's in the z hat direction if we're using cylindrical coordinates. So the z component of angular momentum is m r squared phi dot, and let's divide by little m. So this is the angular momentum in the z direction per unit mass is r squared phi dot. And this is a constant. Let's call this constant little l. This is the angular momentum per unit mass. And likewise, let's call this constant E over m the energy per unit mass, script E. Now let's rewrite these equations, starting with the energy equation. We have 1/2 r dot squared. There's a term minus gm over r. This term is 1/2 r squared phi dot squared, but phi dot is L over r squared. So this is L squared over 2r squared. And all of that is equal to the energy per unit mass, script E. And our second equation is simply phi dot equals the constant angular momentum per unit mass divided by r squared. So these are the equations describing orbital motion in Newtonian gravity. And we can compare them to the equations that describe orbital motion in general relativity. We had them written right here. And you'll notice they have very similar form. In fact, let me go ahead and repeat these equations right below. So we have, in the general relativistic case, 1/2 r dot squared minus gm over r plus L squared over 2r squared minus mL squared over r cubed equals little e squared minus 1 over 2. Now this is just a constant, so let's call that script E. Let me erase this and replace it with script E. So that's just a shorthand for little e squared minus 1 divided by 2. And then our other equations in the general relativistic case are phi dot equals L over r squared and t dot equals little e divided by 1 minus 2m over r. So these are the equations that govern orbital motion in the case of general relativity. And notice they have very similar form. In particular, if you look at the r dot equations in these two cases, you'll see that they have the same form apart from this extra term that we have in the relativistic case. So this is an extra term. But we should also keep in mind that there are other differences between this equation and this equation. In particular, the dot here denotes derivative with respect to proper time, whereas the dot here is differentiation with respect to Newtonian time t. The other difference is the r here is an areal radius. It does not measure proper radial distance, whereas in the Newtonian gravity, r is both an areal radius as well as a proper radial distance. We can now use these equations to obtain a qualitative understanding of orbital motion. In particular, if we look at the energy equation, in either case, it looks like the equation for a point mass of mass m equal 1 moving in a potential with total energy E. So let's first look at the Newtonian case. So the r dot equation is 1/2 r dot squared, so that's the kinetic energy for a unit mass particle, plus an effective potential, which depends on r, equals the total energy E. In this case, the effective potential is minus big G big M over R plus L squared over 2R squared. We can analyze this by drawing an energy diagram. So here's the R axis, here's the energy axis. Now if L is equal to 0, the case with zero angular momentum, this effective potential just looks like a negative 1 over R curve. So that's a curve like this, and it goes on to minus infinity. This is the L equals 0 case. And if L is not 0, what happens is, starting from large R, this term is very small because it has 1 over R squared. So the curve looks just like minus GM over R when R is large. But as R becomes smaller, this term becomes more important. And eventually, for R sufficiently small, this term dominates over this term and becomes a positive 1 over R squared type curve. So this then turns upwards and goes to positive infinity. So this is the case L not equal to 0. So now let's focus on the case with non-zero angular momentum. An elliptic orbit corresponds to energy in this region where the effective particle just oscillates between turning points. So a turning point R1 and a turning point R2. And that corresponds, of course, to the planet coming closer and then farther away to the sun as it orbits. So this is the case of an elliptical orbit. Now if the energy is positive, up here somewhere, then what happens is the body moves inward, reflects off of the potential, and then moves back outward off to infinity. This is the case of a hyperbolic orbit. And the case of a circular orbit is when the effective particle sits here at the bottom of the potential. So this corresponds to a circular orbit where R doesn't change. Now let's look at the relativistic case. The energy equation is 1/2 R dot squared, so that's the kinetic energy of a point particle with mass m equal 1, plus an effective potential that depends on R equals the total energy E. And in this case, the effective potential is minus Gm over R plus L squared over 2R squared minus mL squared over R cubed. So the energy diagram looks like the following. Here's the energy axis. Here's R. If the angular momentum is 0, if L is equal to 0, then it's just a minus Gm over R potential. So it just looks like this. So this is the case L equals 0. If L is non-zero, what happens is the following. For large R, these two terms are both very small, so the potential again looks just like it does for zero angular momentum. But as R becomes smaller, starting from large R, as R becomes smaller, this term begins to become important, so the potential begins to turn upward just like in the non-relativistic case. But then for extremely small r, this term begins to dominate, and it has a minus sign here. So as r goes to 0, the potential turns over and then dives down to minus infinity. So this is the case L not equal to 0. Actually, that's not the full story. This is what the potential looks like when L is relatively large, and by that I mean the absolute value. So in particular, when absolute value of L is greater than square root of 12 times m, the curve looks like this. If L is small, then what happens is these terms, the r has to become very, very small before either of these terms take effect. So the minus 1 over r potential stays valid for smaller r, and by the time r is small enough for these terms to take effect, this term simply causes the curve to dive to minus infinity. So in that case, the curve has a behavior that looks something like this. So for L not 0 but small, in particular L in absolute value less than square root of 12 times m, you have this type of behavior. By the way, it's not difficult to show where square root of 12 times m comes from. It just comes from analyzing the maxima and minima of the effective potential. Now, for the planets in our solar system, L is large. In fact, for Earth, L over m is about 10,000. So the potential has this shape. In fact, we know that should be true because it should look very similar to the Newtonian potential, which follows very close to this curve. The main difference being it continues on to plus infinity. So this would be the Newtonian curve, the Newtonian effective potential. Actually, this part of the potential where it turns over doesn't really exist in our solar system because the surface of the sun is about right here. So this radius corresponds to the surface of the sun. And remember, the Schwarzschild geometry only applies outside the body, so inside this radius, the geometry is something different. Outside, it's very close to the Newtonian potential everywhere. It just differs by this small term, ml squared over r cubed. So just like in the Newtonian case, we have orbits where the energy is negative and the effective particle bounces back and forth between turning points R1 and R2. So these are the nearly elliptical orbits. They're not quite elliptical because the potential is not precisely the Newtonian potential. It has this extra term. We can also have circular orbits where the effective particle sits here. We can also have orbits where the effective particle comes in from infinity, reflects off the potential, and goes back out to infinity. So these are going to be the nearly hyperbolic orbits. I'll say approximately hyperbolic orbits. These are the approximately elliptical orbits. And of course, we could have a particle coming in with even larger energy up here, but before the particle could begin to experience this turnover in the potential, it's going to run into the surface of the sun. Now let's compute the shape of these nearly elliptical orbits. We can start by solving the energy equation for r dot. So r dot is equal to the square root of 2 times the energy minus the effective potential, which is of course a function of r. And that's either plus or minus square root, depending on whether the effective particle is moving outwards or inwards. And we also have the equation for phi dot, which is L over r squared. And we can now combine these to obtain d phi dr equals L over r squared times 1 over square root of 2e minus v effective. And that's either plus or minus depending on the direction of motion. Now integrate this equation. We have the integral of d phi is equal to plus or minus the integral of dr L over r squared 1 over the square root of 2e minus v effective. Now what we would like to do is compute the angle that the particle or planet moves through as it moves from the inner turning point R1 to the outer turning point R2 and then back again. And that angle is just twice the angle it moves through as it moves from the inner turning point R1 to the outer turning point R2. So let's call that angle delta phi, and it's just twice the integral from R1 to R2 of dr L over r squared times 1 divided by 2 e minus v effective. And this is the change in angle that's equal to 2 pi in the Newtonian case. Now let's recall the meaning of R1 and R2. R1 and R2 are roots of E equals V effective, which depends on R. So if we go up to our diagram here, we see R1 and R2 here and here. So these are roots, these are the places where E is equal to V effective, and the V effective is this curve right here. Okay, so here is R2, here's R1, but notice we actually have 3 roots. There's another root right here where V effective is equal to E, and we can call that root R0. Now, of course, this root is inside the surface of the Sun, but from a mathematical standpoint, our calculation of the change in angle doesn't really know that. There are 3 roots to E minus V effective that we have to take into account in doing this calculation. So let's take a close look at this expression we have under the square root. That's 2 times E minus V effective equals 2E plus 2m over r minus L squared over r squared plus 2m L squared over r cubed. So this is a cubic polynomial in 1 over r, and it has 3 roots, and the 3 roots are r1, r2, and r0. So the strategy here is I'm going to factor out the root r0 and be left with the quadratic whose roots are r1 and r2. But before I do that, I need to examine the size of each of these terms because we're going to be making lots of series expansions, and we need to keep track of which quantities are small and how small they are. So to do that, let's return to the Newtonian case for a moment, where the energy equation is 1/2 r dot squared minus gm over r plus L squared over 2r squared equals the energy per unit mass E. And now we're going to consider circular orbits, since we know the planets follow nearly circular orbits. Approximately circular orbits. So what do we know? Well, we know that r dot is approximately 0. We know that for a circular orbit, the gravitational force, the magnitude of the gravitational force, is just the mass of the body times the centripetal acceleration. That's v squared over r. So there's the centripetal acceleration. And we also know that the angular momentum per unit mass is just r times the velocity. So that tells us that we can replace velocity with L over r. So this equation becomes gm over r squared, that's the magnitude of the gravitational force, is equal to m times L squared over r cubed. So now canceling the m's and one of the factors of r, we find that gm over r is approximately equal to L squared over r squared. And now if we go back to this equation, keeping in mind that r dot is close to 0, L squared over R squared is approximately GM over R, so this is 1/2 GM over R. So this is minus a half on the left-hand side, minus a half GM over R. So in other words, E minus 2 times E is approximately equal to these quantities. So just how big are these quantities? Well, if we take Newton's constant times the mass of the Sun divided by the orbital radius of the Earth, we obtain about 10 to the 9th meters squared per second squared. The units of energy per unit mass are meters squared per second squared. So this seems like a pretty big number, but in the world of relativity, it's actually very small. Compare this to c squared, the speed of light squared, which is about 10 to the 17 meters squared per second squared. So each of these quantities divided by c squared is much smaller than 1. Gm over c squared r is approximately L squared over c squared r squared is approximately minus 2e over c squared. These are all much smaller than 1. In fact, they're around 10 to the minus 8. So we're going to consider each of these to be a small quantity of order 1 in smallness. So each of these is an order 1 in smallness. And for example, if I have a product of two of these things, it's of order 2 in smallness. For example, Gm over c squared r times L squared over c squared r squared. That's equal to Gm L squared over c to the 4th r cubed. And that's an order 2 quantity in smallness. As another example, we can take L squared over c squared r squared, which is order 1, and compare it to the square of Gm over c squared r, which squaring this would give us an order 2 quantity. So L squared over c squared r squared is much larger than Gm over c squared r quantity squared. And now notice the r's cancel in this equation, and we can take the square root of both sides, and that tells us that L, or actually the absolute value of L over c, is much larger than Gm over c squared. Let me summarize these results. I don't want to keep writing g's and c's, so let's set g equal to 1 and c equal to 1. What we found is that m over r is an order 1 quantity in smallness. L squared over r squared is also of the same order and small. The energy per unit mass is of order 1. M L squared over r cubed is an order 2 quantity. And we also found that the absolute value of L is much larger than M. Now we can return to our calculation of the change in the angle of a planet as it orbits the Sun. This is 2 times integral from R1 to R2. So this is the change in angle as the planet moves from the inner turning point R1 to the outer turning point R2 and then back again. This is the integral of dr L over r squared times 1 divided by the square root of 2e minus v effective, where this quantity under the square root, 2 times e minus v effective, is equal to 2e plus 2m over r minus L squared over r squared plus 2m L squared over r cubed. And now we recognize this as an order 1 small quantity. All of these terms are of order 1 in smallness, except for this final term is of order 2. And this is a polynomial in 1 over r, and as a polynomial it has 3 roots. And the roots we've labeled r0, r1, and r2. So if you'll remember the energy plot that I made before, so this is the r-axis, and the potential energy has a shape like this. The energy per unit mass has a negative value, something like this. So we draw a horizontal line corresponding to the energy per unit mass. And now there are three roots, a root here, a root here, and a root here. We labeled R0, R1, and R2. And recall the surface of the sun is somewhere between these roots R0 and R1, somewhere in here. So everything to the left of this value of R is not physical, but we still need to take the root R0 into account mathematically. It's still a root of this polynomial. And in fact, I'd like to factor that root out. So let's figure out what it is. When R is very, very small, these two terms dominate this polynomial. So R0 satisfies approximately minus L squared over R squared plus 2m L squared over R cubed equals 0. Just these two terms alone equal 0. And the solution to that is R equals 2m. So that's the R0 root. So now we can write this polynomial 2e minus v effective as 1 minus 2m over r. So this is the root R0. And then these two terms can be written as 2e plus 2m over r divided by 1 minus 2m over r. So that just cancels this factor that I pulled out front. And these two terms are just minus L squared over R squared. So multiplying minus L squared over R squared times this gives these two terms. Now this term 2m over R is a small quantity, much smaller than 1. So we can do a Taylor expansion. So we have the 1 minus 2m over R out front. Then we have 2e plus 2m over R from the numerator. And from the denominator we have 1 plus 2m over R plus higher order terms minus L squared over R squared. So the higher order terms here are of order 2 in smallness, multiplied by either one of these gives an order 3 quantity. So what we're ignoring here is terms of order 3 in smallness and higher. Now let's simplify this a bit. We have 1 minus 2m over r times 2e from 2e times 1. We have plus 2m over r times 1 plus 2e. So that takes into account the terms, this 2e times 2m over r, and also this 2m over r times 1. Those are contained in these terms. And we're also left with 2m over r squared. So that would be 4m squared over r squared. And we have then finally this term L squared over R squared. And this is correct, ignoring terms of order 3 and smaller. Now you'll notice this is just the constant little e squared. Remember, big E was equal to little e squared minus 1 all divided by 2. So let's rewrite this as 1 minus 2m over r times 2 big E plus 2 little e squared m over r. And now let's write these two terms as minus 1 over r squared times L squared minus 4m squared. And finally, let's factor out L squared minus 4m squared and write this as 1 minus 2m over r times L squared minus 4m squared times 2 big E over L squared minus 4m squared plus 1 over r times 2 little e squared m divided by L squared minus 4m squared minus 1 over r squared. So now we have our polynomial, which is 2e minus v effective, written as a product of a linear factor. This is a polynomial in 1 over r, so this is linear in 1 over r, and it has root r0. And we have a quadratic factor with roots r1 and r2. And of course this factor is just a constant. Remember, L is much bigger than m, so this is always positive. Let's use the quadratic formula to solve for these roots, r1 and r2. So 1 over r1 and 1 over r2, it's equal to minus this coefficient, that's minus 2 little e squared m over L squared minus 4m squared, plus or minus the square root of this coefficient squared, so 2 little e squared m over L squared minus 4m squared, quantity squared, minus 4 times this coefficient, which is minus 1, so that just flips this minus to a plus, times this constant term, 2 little e over L squared minus 4m squared. All of that divided by 2 times this coefficient, which is minus 1. Now this simplifies to e squared m over L squared minus 4m squared plus or minus 1/2 times this square root term, and I won't bother to write that again. So these are our two roots, R1 and R2. Actually, they're the inverses of R1 and R2. And now we can write our polynomial in the following way. We have 2e minus v effective equals, let's write this factor first, L squared minus 4m squared. Then we have 1 minus 2m over r, that's the factor that gives the root r0. And then the remaining factors we can write as 1 over r minus 1 over r2 times 1 over r1 minus 1 over r. So now let's put this all together to compute the change in angle, delta phi. This is equal to 2 times the integral from r1 to r2 of dr times L over r squared times 1 over the square root of this whole polynomial. So let's write that as separate terms. We have 1 over the square root of L squared minus 4m squared. We have a factor of 1 over the square root of 1 minus 2m over r. And then we have the remaining factors, 1 over the square root of 1 over r minus 1 over r2 times 1 over r1 minus 1 over r. Let's simplify this. We have 2, and we have the L over square root of L squared minus 4m squared can be written as 1 minus 4m squared over L squared. And actually I've assumed L is positive in absorbing it into this square root term. Times the integral from r1 to r2 of dr times 1 over r squared. And now for this factor, m over r is much smaller than 1, so let's do a series expansion on this and write it as 1 plus m over r plus higher order terms that I'll ignore. All of that divided by the square root of 1 over r minus 1 over r2 times 1 over r1 minus 1 over r. The next step is to change integration variables. So let u equal 1 over r, then du is equal to minus 1 over r squared dr. And our expression for the change in angle becomes delta phi equals 2 divided by the square root of 1 minus 4m squared over L squared. There's a minus 1 from here. The integral ranges from 1 over r1 to 1 over r2 du. This factor in the numerator becomes 1 plus m times u. And the denominator is square root of u minus 1 over r2 times 1 over r1 minus u. Now this integral can be done analytically. You can look up the result. We have delta phi equals minus 2 divided by the square root of 1 minus 4m squared over L squared. And the result of this integral, if we just take 1 divided by this square root term, the answer is minus pi. And then plus m times the integral of u divided by this square root term. And that's equal to minus pi over 2 times 1 over r2 plus 1 over r1. Now the sum of these two roots we can find because we have the explicit results for the roots. When we add 1 over r1 and 1 over r2, the square root term here cancels, and we just have twice this term. So 1 over r2 plus 1 over r1 is equal to 2 little e squared times m divided by L squared minus 4m squared. Let's simplify this result. Let's first cancel the minus signs. We also have a 2 here that cancels the 1/2 here. And what we're left with is delta phi equals 2 divided by the square root of 1 minus 4m squared over L squared. Actually, let's bring the pi out as well. And we have 1 plus little e squared times m squared divided by L squared minus 4m squared. And one more simplification. Let's write this as 2 pi divided by the square root of 1 minus 4m squared over L squared times 1 plus little e squared times m squared over L squared divided by 1 minus 4m squared over L squared. Now let's remember little e squared was equal to 1 plus 2 times big E, and big E is a small quantity of order 1, so that means that little e squared is equal to 1 plus small quantities, and also recall that m is much, much less than the absolute value of L. So this term here is already small by virtue of the m squared over L squared factor. So we can approximate E squared as just 1, and we can also drop this 4m squared L squared term in the denominator, again because the numerator is already small. So what we're left with then is 2 pi over the square root of 1 minus 4m squared over L squared times 1 plus m squared over L squared. And now let's expand this term in the denominator, again because m over L is small. And this is 2 pi times 1 plus 2m squared over L squared plus the higher order terms that we're dropping times 1 plus m squared over L squared. So multiplying this out, we now have 2 pi times 1 plus 3m squared over L squared plus higher order terms that are proportional to m to the 4th divided by L to the 4th. So this is our final result. The change in angle is equal to 2 pi plus 6 pi m squared over L squared plus higher order terms. And this is the change in angle that the planet experiences as it moves from its inner turning point to its outer turning point and then back again. And you'll notice that the leading order piece is just the Newtonian result, 2 pi. So this extra term, 6 pi m squared over L squared, is the general relativistic correction to that change in angle. Let me try to draw a picture. So here's the sun, and here's a planet starting at its point of closest approach. It moves outward. Here's the point in which it's the farthest away from the sun. Then it comes back. Now if this were Newtonian gravity, it would reach its point of closest approach, called the perihelion, after moving through an angle of exactly 2 pi. But in general relativity, it reaches its point of closest approach a little bit later. So here's the closest approach initially, and here's the point of closest approach after an orbit. And the difference in angle here is 6 pi m squared over L squared. So each time this planet goes around, that point of closest approach is shifted by a little bit, by this amount. And that's referred to as the precession of the perihelion. So this correction term, let's call it delta phi correction, the general relativistic correction. And by the way, if we put back in the factors of g and c, this is gm over cl quantity squared. How big is this? Well, among all the planets in our solar system, it's largest for Mercury. So for Mercury, if we take this result, which is the precession, amount of precession per orbit, and multiply by the number of orbits in a century, we get 43 arc seconds per century, where an arc second is 1/60th of 1/60th of a degree. So that's, of course, a very small amount, but it's actually measurable, and it was measurable as long ago as the 1800s. So that was when it was first measured. And this was a real puzzle at the time because people couldn't understand why there was this anomalous precession of the perihelion of Mercury. And it wasn't until general relativity came along that we had an explanation for this. In fact, this precession of Mercury's perihelion constituted one of the first experimental verifications of general relativity.